So, good morning to the world. Welcome back to the second day. We have now a block with 5 presentations from people outside the core team and showing what they're doing, how they use NGSolve. Mainly outside the core team, except one.
Okay.
The first one is Siyar Dumans, working with Florian Liebig, who's a professor in physics, and showing the simulation of graphene. You have seen also the poster blitz notebook by Siyar yesterday, and you can look into this if you want to see a starter and talk to him.
Okay. Thank you, Achim. So I'm going to talk about bilayer graphene devices, which have nice electronic properties, which people study in experiments. We're physicists, so don't expect any sophisticated math. So graphene, this is an artist's imagination of graphene. Graphene is just a 2-dimensional lattice in a honeycomb shape. And in each vertex of the lattice, you have one carbon atom. This has very unique electronic properties, and its discovery was awarded with a Nobel Prize. And bilayer graphene is just 2 of these graphene sheets stacked upon each other. Right, and people use this to build electronic devices, such as this. So this is a scanning electron microscopy image of a bilayer graphene device by Christoph Stampfer group at Aachen. So what you're seeing here is a set of gates. These are the gates. This is insulating material, actually, because this is the top view, and below the insulating material there is bilayer graphene. And what people like to accomplish in this experiment is they want to very precisely induce one electron, let's say, or one hole. So hole, for those who don't know, hole is basically, you can attract electrons, but if you change the sign of a potential, you can also repel them. And if you repel them locally, that's almost like a positive charge. So that's what we call a hole. But the thing is, people only measure this arrow in experiments. So what you see, what is indicated here is electric current from left to right. And people really don't know what the electrostatic landscape here is. This is why they come to us. They ask us, well, how does my electrostatic landscape actually look like? This is quite important because the only measure that they have is the current, and they for example, observe that you can move this hole up and down, for instance, or you can deform the channel, and these are quite hard to understand just by looking at the current. And secondly, these devices are very expensive. They take a lot of time to make, and the failure rate of such a device is like 50%. So if you do 10 devices, 5 of them die somewhere in the production process. And this device is actually almost dead. There is a short circuit here. So this gate and this gate touches, so you can't actually use the lower half of the device. So instead, what we do is we just simulate the upper half with NGSolve. So what it looks like in practice is like this. This is the electrostatic potential solved once. So these are the electronic gates. They are basically our Dirichlet boundary conditions. This line here is bilayer graphene. It's atomically thin. It's just one line, like 2 or 3 angstrom. And all this stuff, this is insulator, this is an insulator, this is aluminum oxide, but all this stuff is just there just to manipulate 1 or 2 electrons inside this sheet of bilayer graphene. Right, so what's the precise problem statement? And it's Poisson's equation. So we have a set of insulating materials with different permittivities. We have the Laplace operator acting on the electric potential, which gives us some charge. And typically, you solve for the electrostatic potential for a given rho. I mean, this was at least the case in my education as a physicist. You are given the charge, and you are asked to solve the Poisson equation, find the potential. Out of the potential, you can calculate forces and energies. Here, it's a bit different. So from experiments, we know that the charge is a function, actually, of the electric field and its gradient. And here, you are not given the right-hand side. So you have to solve for both the phi and the rho. And going forward, I'm just going to call this expression the rho the model. So I don't really have time to get to nitty-gritty details of the model. But essentially, we are just counting the number of electrons which are able to conduct. There is a precise definition of this. So we are just claiming the number of electrons is also a function of phi and gradient phi. And I'm just going to claim this number operator is just an integral over the density of states, and density of states is, if you are given an Hermitian operator, you can calculate the energies, you can order them since they're real valued, and the density of states will just tell you the distribution function of the eigenvalues. Right. And this model is called LDOS, so this is density of states, and LDOS stands for local, because for each point in the Balia graphene sheet, the density of states can be different. Yeah. And this is the right-hand side for graphene. I pointed this out yesterday. The right-hand side for these kinds of devices are pretty ugly. So what you see is this blue line is if the gradient is 0. So by the way, when I say gradient, it's like a misuse of notation. I mean the out-of-field gradient. I don't mean the in-plane. So if the out-of-field partial derivative is 0, you get a nice line. But if you increase the partial derivative, you have a gap opening, and then you have these kinks. Right. So as I said, you typically solve for phi given a rho, but here both are unknown. So what do? You just restate the problem very basically. You say, okay, right, so pick one row, maybe correct row, maybe the wrong row, but doesn't matter. Then you solve for the electric potential. So this is NGSolve. NGSolve does this for us. We provide it with a row, and it gives us the phi back. Right, and then we are going to just claim if rho was correct, then if I evaluate the model with this phi, given this rho, then the phi that I plugged in and the model that I get out is the same. So I'm going to claim that the model is the true rho of the system. And I'm going to claim the system is solved if the model and the income in the row you input is the same. Right, and if rho was the wrong choice, then they're not going to be equal. In fact, there's going to be a difference. And I'm going to say we are just going to minimize this difference, or rather we are going to find the root of this function rho, delta. Right, and we are just using pre-existing root finding methods for this. Right, so very short overview. You're all experts, but I still have to say this. So you just define so how to do this. There is a notebook. I tried to show it in 2 minutes yesterday. But you just define your functions. You set up your trial and test functions. You set up your bilinear form. You assemble it, and you invert it once, and you keep it, because you're going to need this later. You don't need to keep inverting it. Then you call the root finder. Inside the root finder, you evaluate the given row of S on a certain set of points Ri on the bilinear graphene sheet. And this you can interpolate inside NGSolve with the Voxel coefficient method. Yeah, and then you define linear forms, you set the boundary conditions. You have a right-hand side, and you just run the root finder until delta is sufficiently small. Right, so a word on root finding methods. Things like Broyden don't work here, because you can't linearize the function around this kink, obviously. So this is a problem. I found that, so I just tested all the SciPy implemented root finders. I did not do really a lot of work on this. I just used what was there. And DF-SANE stands for derivative-free spectral algorithm for nonlinear equations, and this works, actually. Yeah, I provided a notebook yesterday. It's on the GitHub if you want to have a look. I also showed you this. So this is the first iteration. For the first iteration, the root finder needs to have a starting point so that it can do its magic. I just evaluate the right-hand side 0. So I use the homogeneous solution. And then I go into the model, and this gives me some starting row. And then this is then the model, and this is then the difference. And the aim here is to find the correct row such that the row that you put in and the row which the model tells you is approximately 0, which happens here at 27 iterations. Right, so I showed you the device at the beginning. I can show you now a few cross-sections in this bilinear graphene sheet. So the only dependence that's relevant here is the x and y in-plane dependence. The z dependence is not super important. This is basically the solution. This is rho. These are some electrons flowing left to right. And this is kind of unfortunate, but there are actually some positive charges in red. I don't know if you can see this in the back. I'm very sorry. I should have thought about this. But there is some red dot here, and there's some blue dots here. Yeah. Okay, so in words, for a physicist, what does a nonlinear Poisson equation actually do? So this green line is the solution for the homogeneous problem if the right-hand side is just 0. And the magenta line is what you get out of the Poisson solver. So basically, the statement here is you never have as much phi a magnitude of phi as you think you have. You are actually just overshooting. So if you think you have 60, in reality you have a lot less, about 20, because you have some charges in the model. And my very last slide, so I just put this on yesterday because I was very impressed by the math talks. And I thought to myself, well, I have a room of experts here. Maybe I should just ask. So the model LDOS is good in the sense that you can explain experiments. So experimenters come to us with some curves, and we can explain them roughly. But these are just qualitative explanations. The full treatment of this problem would actually require us to solve an eigenvalue problem on the fly. In particular, we would have to diagonalize this operator. So this is a 4 times 4 operator. It's defined on each point in bilayer graphene with some diagonal potentials. And these pi operators, pi is a partial derivative in x minus the imaginary unit times partial derivative in y. And this is the next step for us. So we have to solve this somehow. And if there are any ideas from you in the audience, please let me know. This has to be, so if I will try to solve this with finite element methods first, and if it's not working, I'm going to try something else. But I have a feeling it should work. I hope. Yeah. Okay, thank you.
Thank you, Siyar, for the nice presentation. Time for 1 or 2 questions on. Yeah.
Okay.
Yeah, it's showing an interesting application in computational physics, combined NGSolve with solvers developed in your group.
Thank you.
If you are interested in either the physical part or also in the coupling, how the coupling of NGSolve with your models are done, talk to Florian or Siyar on this during the day. Okay.
Thank you.
Thank you. Yeah.